So this Mordor, we're going to take a deep dive into fibers, what they are, how they work together, and how come they're kind of cool. So let's start out just what are fibers? They're known by a lot of different names. You can call it cooperative threading. So back on old versions of Mac OS, the threading was not preemptive. They were always cooperative. So you can compare fibers to cooperative threading. They're also known as coroutines, which let you go back and forth between two functions calls. The classic example is a producer-consumer down here, where the producer doesn't have to rearrange himself to make it easier for the consumer, and neither does the consumer. Each one just returns and keeps yield returning a return value, but doesn't actually exit the function until it's done. They're also known as stack swapping because it's swapping the stack in user mode. It's threading outside of the operating system's level. So it's also called user mode threading or M-on-N threading, which means that you're using N kernel mode threads, but you have M operating threads or fibers. So in Mordor, I just call them fibers, go with a single term there. And they can be very useful for yielding instead of blocking. So when you want to go do the network or do a disk operation in a classic thread, that will block, and that thread can no longer run. And the kernel you have to do a swap into kernel mode, and the kernel mode has to figure out which thread to run next, and then swap that. And then at some point in the future, you get swapped back in. So by yielding instead of blocking, you say, I know this is going to block. I'm going to start the operation, and then I'm going to explicitly let some other fiber take over this thread so that the kernel doesn't even know that it should swap out or anything. They're very useful because they're very concurrent. Threads have fairly high overhead. The worst performance hit is the context switching. When you have thousands of threads that a kernel is scheduling preemptively, you get swapped out all the time when you don't want to. And kernel mode context swaps are a lot more expensive than doing it in user mode. So because of those issues, you can have thousands of fibers because it's much faster. You control when it swaps. The one thing is, each fiber does have its own stack, just like a thread, but it doesn't actually utilize memory until it hits it. So you'll use a lot of virtual memory, but not any physical memory unless you are actually using that memory. And the other thing it's used for is producer-consumer, the coroutines. So iterators or generators in Python are very, very easy to write with fibers or coroutine model, as opposed to having to keep a state machine in your object. So fibers versus threads. Sometimes it's hard to contrast them because fibers have a lot of the same properties as threads, but they exist at the same time. So every thread, when it starts, has exactly one fiber, and that fiber represents the stack for that thread. So in essence, the stack belongs to the fiber, not to the thread. There's exactly one fiber that runs on a thread at a time. The operating system doesn't schedule the fibers, but it does schedule the threads. The fibers get to schedule themselves outside of the purview of the operating system. And when a fiber exits, if it's the root fiber for that thread, then the thread will exit also. And then one other thing to keep in mind is thread local storage is per thread, and fiber local storage is per fiber. And that may seem obvious, but you need to keep it in mind that because fibers don't necessarily have to stay on the same thread, when a fiber is not executing, its fiber local storage goes with the fiber, but the thread local storage stays with the thread. So the main methods for fibers are to call and to yield, and that's called asymmetric fibers or asymmetric coroutines because you use two different methods to transfer control from one fiber to another. So when you call a fiber, you're saying one fiber, I want to call another fiber, and I want you to execute on this thread. When you're done, you need to yield control, and it will go directly back to me. So that creates a stack that the called fiber has a link back to the calling fiber. And no other fiber can touch that calling fiber while it's waiting for the yield. The other method is yield to, which is called symmetric coroutines, which yield to just says replace me with you, and there's no return link there. So I've got a pretty cool animation that shows it. So we have our big process here with our main thread and the fiber that starts out. You have your fiber that's always there. And we want it to create a second fiber. And we're going to call it. So that shows that fiber 2 is now executing on thread 1, but it still has a link to the first fiber. We'll create another fiber, and this time we're going to use yield to, which makes fiber 3 the one that's executing on this thread. And fiber 2 is no longer executing, it just kind of gets moved off, but it still retains the link to fiber 1. And so that when it does get executed somewhere else and yields, it still returns to fiber 1, because that's what fiber 1 is expecting, is that fiber 2 will yield to it. We're going to start up another thread here, which comes with its fiber that comes with it. And fiber 4 is going to yield to fiber 2. So fiber 2 is now executing on thread number 2. If it were to access thread local storage, it would access thread local storage of thread 2, not thread 1, because it's executing. But if it had set fiber local storage while it was executing over here, it would have the same values over there. And then the final one is fiber 2 is going to do a regular yield, which returns control to fiber 1, which is now executing on thread 2. So that just kind of helps visualize how control gets transferred from between the different fibers. So a few other fiber features. There's an implicit yield on return. So if a fiber exits and it has a link to somebody that called it, it will do a yield at that point. So you don't have to call yield explicitly. Exceptions are transported. So if an exception happens on a fiber and it does have a yield on return fiber to know who to go to, that exception will be rethrown in the calling fiber. And it will go across those two fibers. And then fiber local storage we talked about. So on some operating systems, like Windows, has explicit support for fibers. It's built into the operating system, has been around since, I can't remember if it was NT4 or Windows 2000, but they've recently added fiber local storage, which makes it so that I don't have to do any of the hard work in Mordor. On other platforms that don't have native support for fibers, it's implemented inside of Mordor as an array that's associated with the fiber object, just how you would think it would be.